Okay, so let's start today's session. So I'm Anand Singhal, a PhD student from IIT Jodhpur. I'll be assisting you in solving the problem for the course Digital Electronic Circuits. This session will be for week 6, and I'll be assisting in solving the similar assignment problems as in week 6. Assignment problem given by NPTEL, and this course is taught by Professor Gautam Saha. So in the previous weeks, as the course outline says, we have almost covered the combinational circuit part completely, and by this week we will be closing the combinational part totally. So this was the combinational part. The first 6 weeks belongs to the combinational circuit of the course, and the last 6 weeks basically belongs to the sequential part. So this is quite important, and we'll be starting it in the subsequent weeks. And today, we in the week 6, we'll be wrapping up the combinational part. With a few of the left topics that are carry look ahead adder, magnitude comparator, ALU, that is arithmetic logic unit, error detecting and correcting codes. So there are these few topics that we'll be covering in this particular week, and by this we'll be concluding our combinational part of the course. And after that, we'll be starting for the sequential part. So before starting this particular question, in the last week we were left with a single question for the 2's complement, which was something like, so I'll be solving that particular question, and then we'll be starting with the topics of this week. So the question was, if you have not done, so I'm just doing it again. Given the binary numbers, so there were two numbers that were given, that was x, which was 1010 and y was given by 1 4 times o and double one. So we need to find, first was x minus y and second was y minus x, and both we need to find using 2's complement method. So this was the question which was left in the last week, that is the week 5 topic of 2's complement. So I'll be covering this particular question, and then we'll be moving ahead to the topics of this week. So the basic terminology is, so let's start the solution. So the basic terminology is basically, if we need to subtract y from x basically, so what we can do is, using 2's complement method, we can add the 2's complement of y into x, not 2's of x, that is a 2's complement of x, and this will give me the subtraction. Similarly, if I need to subtract x from y, then what I need to do is y plus 2's complement of x. And there are also two possibilities of getting a carry and not getting a carry of the final solution. So getting a carry, and there are two methods. So both of these particular question, x minus y and y minus x, will define, one of them will be having a carry and one of them will not be having a carry. So I'll teach you how to compute these subtraction using the 2's complement method. So let's start the question again. So the first question is x minus y using 2's complement. So I need to write x and y, so I'm writing them. It was 1010 100, and y is 1 4 times 0 and I guess double one. Yeah. So first of all, what we need to do is, as we have already discussed, I need to compute the 2's complement for x minus y. I need to add 2's complement of y into x. So, first of all, I'm computing 2's complement of y, which is nothing but, so we have a y which is 1 4 times 0 double one. So to start that, what we need to have is, we need to have the ones complement first. So here is the ones complement of that particular number. So ones complement of y will be, so those who have just joined, I am just repeating the last week's last question, which was given as a homework problem for x minus y and y minus x. So I'm doing the first part of x minus y, which is basically x plus 2's complement of y. So I'm doing the 2's complement of y right now, for which I need to compute 1's complement of y, that will be 0, 4 times 1, 0, 0. So if you have done the question in the last week, if you have the answer, you can type in the chat box. So here is a 2's complement of y. It will be 1's complement plus 1, as we already know from the last week lecture. So this is 0, 4 times 1, 0, 1. Now to compute final x minus y, we need to add this 2's complement of y into the given x. So for doing that, I'm doing x plus 2's complement of y. Let's say that is z. That will be, first of all, I need to write x 1 0 1 0 1 double 0. I guess this was x. Yeah. And 2's complement of y we have just computed, it is 0, 4 times 1, 0, 1. So what we need to do, we need to add them now. So I'm doing the same. 0, this will be 1 and 1, 0, this will be 1, 0, 1. So you can see we have got a carry here. This is the just basic binary addition. So once we get, so there are two possible cases, you will be getting a carry or you might not be getting a carry. So if you get a carry, you need to just discard the carry, and whatever is left will be your final answer. So x minus y using 2's complement method will be 0 0 1 0 0 0 1. You can also write it in the decimal form. So 0 denotes negative, and this is 0 1 2 3 4. So this is minus 17. So if we try to do the second case, which is y minus x, so for sure this one will be not getting a carry. So we will look ahead at how to solve the problem which we don't have a carry further. So let's compute that also. So now doing the second part, which is y minus x, and x and y we know. So this will be equivalent to y plus, now we need to do the 2's complement of x. So 2's complement of x, so first of all I'm writing x, which is 1 0 1 0 1 double 0. So to find out the 2's complement, first will be the 1's complement of x, that is 0 1 0 1 0 1 1, and 2's complement of x will be this plus 1. So I'm doing it 0 1 0 1 0 1 1 plus 1. Sorry. So this will be the 2's complement of x. So now I'm doing what? I'm doing to find out z, I'm doing y plus 2's complement of x. I'm doing it. So y is, I forget what is y. Y is 1 4 times 0 double 1. And we have just found out the 2's complement of x, that is 1 0 1 0 1 double 0. Okay, let me see if I've done it correctly. So 1 0 1 0 1 0 and 1 1 is 0. Then 1 and 1 is 0. This is 1. Okay, so I have written it wrong. Sorry. This will be 0 1 0 1. Yeah. So I'm just writing the correct thing, 0 1 1 0 0. So if I add now, this is nothing but y plus 2's complement of x. So this is 1 1 1 1 0 1 1. So you can see there is no carry, that is there is a 0. So now in this thing, if you don't get a carry, what you need to do is you need to compute the 2's complement of the final answer again. So you need to have again find the 2's complement. So I'm doing it again to find out the 2's complement of this final digit again. So this was basically, I'm repeating, so this was y plus 2's complement of x. We have received it, but we are not getting a carry. So in this case, you need to compute 2's complement of the answer again. See, this is a very important concept, so please be aware here. of the answer again to get the final answer. So this is not the final answer. So what we'll do is we will compute the 2's complement again of this 1 1 0 1 1 1 1. So 1's complement will be inverted and 2's complement will be plus 1. So 0 0 1 0 0 0 1. So now you can still see we are getting the same answer. If I do it in binary, then minus 17, which was a case for this also. So again, to make it clear, there were two cases. One is getting a carry, one is not getting a carry. So once you get a carry, you can just directly discard the carry and that will be your final answer. But if you don't get a carry, you need to compute 2's complement again. Whatever you have got without carry, you need to compute the 2's complement of that answer again to get the final answer. Is there any doubt in this? How to do a subtraction using 2's complement? Please type in the chat box if you have any doubts. You can take a look. Maybe we can start the next problem in 2 minutes. Is there any doubt in this? Please respond in the chat box. Is it clear, everyone? Please do respond in the chat box. So as we discussed, now we'll be starting with this week's topic. That was for week 6. We have some adders, some magnitude comparators, some ALU, that is arithmetic and logic unit, and some of the error detecting and correcting codes. So let's start with these topics now. So we have a circuit Okay, so this is the first question for this topic for this week's, which says in the figure below the outputs F1, F2, F3 respectively. So these are the outputs you can see F1, F2 and F3 respectively. What will be these values when x is 0 and y is 0? So I have a x is equals to 0, I have a y is equals to, sorry, 1. So we need to find out what is F1, F2 and F3. So maybe you can give it a go. You can take 2 minutes and then I'll solve it, because this is very basic, just circuit realization problem. So you can tell me whatever F1, F2 and F3 you are getting, and I'll solve it in 2 minutes. Quickly, you can let me know. Any answer, anyone? Please try to respond. Any answer? Did you try? Yes, so fine. So basically, we have this circuit and this circuit. Okay, I've got answer as F1 is 1 and F2 and F3 are 0. So let's check if this is correct. So this circuit is basically a 2-bit magnitude comparator. Magnitude comparator means we have 2 bits, let's say x and y. So there can be three cases: y will be greater than x, y can be equals to x, and y can be less than x. So basically, when y is greater than x, then f1 will be high. That is, this is for y is greater than x. then we have a y equals to x, then f3 will be 1. So basically this is for x equals to y. And when when y is less than x, so this f2 is 1. And rest of them are 0 for each of the cases. So let's also try to find out the relation. So this is x and this is y, and this is getting NAND. And okay, so if you know that we can make this circuit as in the AND or implementation part, we can make this circuit like this, and we can cancel out these buffers. Oh, sorry, not buffers, this NOT gates, not this one, but this one. Yeah. So now we have a x bar here, we have a y complement here, and since we have cancelled, so we have a xy here, and also we have a xy here. And we can know x plus x bar y will be x plus y. So here I have a x plus y. Here also I have, yeah, here also I have y bar plus y z is. Here I have a x bar plus y. Here I will be having a y bar plus x. Because of the property that a plus a complement b is a plus b. So in the first, the below one, I am getting x complement plus xy. So this will give me x complement plus y because the complement is present here. So this one is x complement plus y, this one is y complement plus x, and finally in between we have the NAND and the again NAND. So two NAND is basically, this is a NOT gate. So if I do the NAND of this thing, so this NOT and this is completely getting cancelled, and F3 is just the multiplication of these two things. So I'm doing that. So this will be x, y, sorry. Okay, I can write maybe in the next page. This is, so x bar plus y times y bar plus x. So this is basically F3, which is x bar y bar plus 0 plus 0 plus xy. So this is basically x nor y. So we have the relations also now. For F2, we have y bar plus x, or is it x bar plus y? Sorry, this is x bar plus y. For F1, we have x plus y bar. So you can now clearly see that when y is 1 and x is 0, this was the question. So x is 0 and y is 1. X is 0 and y is 1. I have written it wrong. This is x bar and this is x y. X bar plus y, yeah. Okay. And f1 is this. Y is greater than x, so f1 will be 1. Maybe I'm getting this time. So if I now put what is the question? X is 0 and y is 1. So basically they are not equal, so x nor will be 0. Then we have a y as 1, so this is the complement, so 0 plus 0 will be 0, and 1 here we have a y1, so 1. So this is how we are getting f1 is 1 and f2 and f3 are 0. Okay, so I have an answer. Yeah. So basically this is a magnitude comparator, and you need to see whatever the question has been asked. So instead of doing all this calculation, if you would have known that this circuit is a magnitude comparator, then you know that this will be 1 when only x is equals to y, this will be 1 when y is greater than x, and this will be 1 when y is less than x. So we can directly say, because y is 1 and x is 0, so y is greater than x, so f1 will be 1 and rest will be 0. So this is how you can directly arrive to option A, which is the direct method or very quick method to solve this problem. So this is one of the important topic of this week's lecture, which is a 2-bit magnitude comparator. Is it clear, everyone?
Yes, sir.
Okay. Okay, so this is a theoretical question. Let's move ahead in this also. Uh, Now you need to be aware that it is asking for which of the statements are false instead of true. So we need to check first of all the statements. So the first statement is gray code is a sequential code. The second statement is ASCII code of capital A is this and small a is this. Then we have for XS3 code, the allowed values are from this range to this range, and binary to gray and gray to binary are only done using XNOR gates. So these are all the statements. So let's start one by one. So the first statement is gray code. So as you already maybe read in K maps also, that gray code is a sequential code, that is there is only a 1 bit difference. Sorry. In each consecutive digit, there is only a 1 bit difference that makes the gray code sequential, that we have already studied in the K maps also, that the K map we made on the basis of gray code. Let's say 0, 1, 2, 3. So for a 3-bit code, what we do is we made 2, 3 instead of that, we made 3, 2 because the gray code is like complementary here. Then 4, 5, 6, 7, it is like that. To make a difference of 1 bit in the each of the consecutive bits, so gray code is a sequential code is correct, and we need to check which of them is false. Now in the ASCII code, so this is purely theoretical. So ASCII code of A is 1, 5 times 0 and then 1, and small a is it just this one is replaced by another one. So similarly for B we can check, and this is completely theoretical. For B we have a certain code in which we have an extra one maybe here and here. So we will see this in some other question. What are the ASCII code? So this is also correct that ASCII code of capital A is this and small a is just a extra one in the second most significant bit. And for XS3 we know XS3 code is nothing but when we have a BCD we convert them to plus 3. So for BCD of 0 it is 0 0 0 0. It is equivalent to 3 in that, so it is 0 0 1 1. Similarly 9, which is 1 0 0 1, is plus 3, that is 12, that is 1 1 0 0. So this is the XS3 code which ranges from 3 to 12 basically, from 0 0 1 1 to 1 1 0 0, which is given in the question. So this is also correct. Now the last question says, sorry, the last option says that binary to gray and gray to binary conversion are done using XNOR gates, which is wrong because we need XOR gates instead of XNOR gates. If you are aware of this concept, so the binary to gray or gray to binary conversion is basically done using the XOR gate. So this statement is completely wrong. So out of all these four statements, only this statement 4 is incorrect, and now we can see the options. So option D will be the right answer. Is there any doubt in this particular problem? Anyone, any doubts?
No, sir.
Fine. So then we can move ahead. Maybe you can take some time to solve this. This is a good question. So this is a ALU block which is given in the question. And in the following block, you have been given when S is 0, then what is the y0 and y1, and when S is 1, what is the y0 and y1. So what will be the simplified expression for y0 and y1? So this is a ALU block. ALU is basically a arithmetic and logical unit. So you can see this something like a multiplexer but with multiple outputs. And you can try this out. I have given you a hint. You can treat this as a multiplexer with multiple units, multiple outputs. And then maybe you can find it out, and then I'll solve this also. So maybe you can take 2 3 or 5 minutes also, and let me know what are the possible options that you are getting. Okay, so you can try it. Maybe side by side I can also try. So now in the question it is clearly written, if S is 0 then y naught and y1 will be this, and if S is 1 then y naught and y1 will be this. So what I can treat it as, so if S is 0, and there can be two cases if S is 1, right? So for S is 0, y naught is given and y1 is given. So what I can write is, when S is 0, that is S cross, the final output of the ALU will be S bar y0 plus y1, and when S is 1, then it will be y0 plus y1. So this is the basic output of this particular circuit that will again give me y0 plus y1. So what I need to do is here, so, so what I can do is I can directly calculate y0 now because of the inputs. So y0 will be, when S is 0, you can see when S is 0, y0 is this, when S is 1, y0 is this. So be aware here. So when S is 0, I'm calculating A. Sorry, when S is 0, this is S complement, then y0, which is AB whole complement, and then again for y equals to 1, we have A complement B plus AB complement. So for the first part, that is y0, let's delete this out. So now you can, now it is maybe a bit more clear. So S bar 0 plus SY0, maybe I can write here S is 0, here S is 1. This is how you will get the simplified expression for y0. Does it make sense? This particular expression, S bar is basically when S is 0, and S is because when S is 1. Does it make sense? Is there any doubt in this particular expression that I have written?
No, sir.
Okay, so now let's try to solve this. So y0 is S complement, then we have a complement plus B complement. So I've opened it, the first bracket, and finally we have S and this thing. So I'm opening it completely now. S complement A complement plus S complement B complement plus S AB complement plus S AB complement. So now I'm taking A complement common from this and this term. So this will be S complement plus SB, and from the rest of the term B complement, then it will be S complement plus SA. Can anyone tell what will be this simplified? S complement plus SB will be
S bar plus B bar.
S bar plus B, not B bar, right?
Yes, sir.
Similarly, this will be S bar plus A. So now what I will do is I'll just open it. This will be S complement A complement plus A complement B plus S complement B complement plus A B complement. So this is a simplified expression for y naught. This will be one of the option, I guess. So S complement A complement, then S complement B complement, then A complement B. Yeah. So we are getting y0 as this C option. So we might not, we have, I guess, already got the answer because there is only one option in this in which there is this y naught. So, but just for the sake of the conceptual clearance, we will also calculate this y1. So I'm calculating the y1 also now. So y1 will be basically S complement when y1 is, when S is 0, and S when y1 S is 1. So S complement times when y1 is, when S is 0, y1 is this term, which is A plus B whole complement, and it is AB when it is 1. So I'm just writing A plus B whole complement, and here it is AB. So this is very simple. So this is A complement B complement plus SAB. This will be y1. So we can check in that option only. Yeah. So this is S complement A complement B complement plus SAB. So option C is the correct answer here. This is how they frame the ALU questions, I guess. This is similar to your assignment problems also. Is there any doubt in this now? You can take a look if you have any doubts and let me know if you have any doubts. Okay, maybe you can try the next question out. Maybe you can take 2 minutes if you know the answer. You can type in the chat box and then I'll solve it. You can take 2 minutes. Okay, so let's try this out. So this is in the given figure it is written the output can be given by. So there are three, you can clearly see there are three outputs that are x greater than y, equals to y, and less than y. So again this is a 4-bit 2C, C means complement basically. So this is a 4-bit 2's complement subtractor which has its certain conditions. So I'll write out those conditions basically. So it has a condition for x greater than y, we need to have a C out of 1 and either of S3, S2, S0 and S0 should be 1. I've written either of. So any one of them if it is 1 and C out is 1, so the output will be equals to x greater than y. Similarly for x equals to y, we need to have C out as 1 and all of S3, S2, S1, S0 should be 0. And the last is when x is less than y, C out is 0. We don't even care about what is this S3, S2, S2, S1, S0. If this C out is 0, we can directly say that x is less than y. So these are the three basic condition of this 4-bit 2's complement subtractor. So if you try to write it in the form of expression, so for x greater than y, what we can write is, let's say that is z, z1 maybe we can write that C out is 1 times either of this is 1, either means or operator, so s3 plus s2 plus s1 plus s0. So if either of them is 1 and C out is 1, this x greater than y will be 1. Is this clear, this statement that I have just written? Any doubts in this statement?
No, sir.
Okay. So similarly, I can write for x equals to y, maybe z2 I can write. So C out is 1 and all of them should be 0 means all of them should have a
Yes.
bar to make it the complete statement as 1. Similarly, for x less than y, C out is 0, so we can directly write C out complement. Once we have a C out complement or we have a C out as 0, this will turn out to be 1. So these can be the expression for the given particular what is this combinational logic. So for x greater than y, we need to have C out times either of them as 1. So you can see maybe, yeah, so in these two options, maybe in these three options, so option C is eliminated here because it has a C out bar. Then for x equals to y, we have C out and then all the complements. So here it is C out and all the complements. And yeah, so I guess option B will be the correct answer. And then for the last, we have C out complement. Yeah, so option B will be the correct answer. So you need to learn these things, that how this 4-bit 2's complement subtractor work and what are the terminologies. So this is how it is. The answer is B. You can check it out and maybe we can try the next problem in 2 minutes. And you can tell if you have any doubts. I hope this is clear. So maybe you can try the next problem out. This is basically a the gray code of this is denoted by x. So if we feed x to a binary, or basically a binary to gray conversion, so maybe you can try it out. You can take 2 minutes and then I'll also solve it. Any answer? Okay, so we have already read the concept of how to convert a octal number to binary or binary to octal. So here the gray code of binary, basically x is the gray code of 125 to the base 8. If we feed x to a binary to octal converter, so we need a binary, right? Then what will be the output? So this output is now unknown. So first of all, we need to convert this into the gray code. So I'm just directly writing the binary version. So 1 is 001. This we have already done in the last classes also in the number system lecture. So 2 is 010 and 5 is 101. And now to, if I guess you already know, for binary to gray, what we need to do is, can anyone tell?
The first bit will remain same, and then you
Yeah,
need to XOR.
yes. Basically, the first bit remains the same, which is a 0, and then we need to XOR the consecutive digits. So 00 is 0, 01 is 1, 10 is 1, 01 is 1, 10 is 1, then 01 is 1, 10 is again 1, and 01 is again 1. So now this is the gray code, which is fed into a binary to octal converter. So we have already done that. To convert a binary into octal, what we need to do is we need to make them in pairs again, and whatever the number we are getting will be the final octal lead. So this is 001, which is 1, 111 is 7, sorry, and again 111 is 7. So this will be the final output of the binary to octal converter, which is option C. Is there any doubt in this? Anyone? So if you don't have any doubt, let's say let's do an example quickly. So let's say I give you 251 maybe. Instead of 125, not 251, wait. Let's say okay, 251 only to the base 8. X is basically again the gray code of 251 to the base 8, and you need to find out the octal number. So quickly let me know what is the answer. You can take 2 minutes now because this is very easy, and type in the chat box. So I've got answer 375. So let's see. So I'm writing quickly. So this is 2, 5, and 1 is 001. So I'm doing it gray now. So 0 remains same. Maybe I can use some different ink. 0 remains same. Then 01 is 1. 10 is 1. 01 is 1. 10 is 1. 01 is 1. 10 is 1. Okay, I guess I have. And then 00 is 0. And 01 is 1. 1, 2, 3, 4, 5, 6, 7, 8, 9. Yeah. So again making pairs in 3, 3, 3, 3. So I have a 011, which is 3. I have a 111, which is 7, and 101 is 5. I guess this is the answer. Hmm. So 3 and 5 will be the answer. Is it clear to everyone? Any doubts in
Yes,
this?
sir.
Fine. So let's move ahead now quickly. So now, okay. So we have two 128 bits binary codes of X and Y are to be compared by. Okay. So this is again a knowledge based question that you need to have. So this is a IC 7485. So you need to be aware that this is a 4-bit magnitude comparator. You need to learn the name of the IC and what it does. So this particular IC is a 4-bit magnitude comparator. So this IC can take 4 bits at a time. So now the question says we have a 128-bit binary codes. So we have two 128 bits binary codes X and Y, and for this conversion or comparison of X and Y, how many such ICs are required? So you know that one IC 7485 can do a 4-bit comparison. So for 128-bit comparison, you need to have 128 times 1 by 4, because a single IC can have 4-bit comparison ICs. So this is a very easy question. This is 32, I guess. Yeah, 32 ICs 7485 will be required for 128, because one is only doing a 4-bit comparison. So this is a direct question and the answer will be option B. I hope there is no doubt in this, because this was a direct question. Is there any doubt?
So they're telling two 128 bytes.
Yeah, so the numbers are 2 bits. So you need to compare two numbers, right? So this is a 4-bit magnitude comparator, means X and Y will be 4 bits each. Then only it will
Okay,
work.
sir.
Yeah. So is it clear to everyone? So maybe we can proceed ahead and I'll give you some time on this. So you need to calculate which of the following expression correctly matches with the output Z. So let me like zoom it out to get you a better overview. So take maybe 2-3 minutes and let me know if you are getting some of the answer, or maybe 5 minutes you can take to solve this out. So let me also try it out simultaneously. So in this question what we have is, we have Z, which is a mux, and we have like 4 select lines for a 16 cross 1 mux basically. And this A1 A0 is getting converted to a single bit A, and this B1 B0 is converted to a single bit B as shown in the figure here. So what is Z? So we need to just clearly see that when will this Z be 1. So there are two lines you can see. This is one line, this is 0 line. So Z will be 1 when all the ones are connected basically. So this is connected to 0, 0, 0, 0, 0 is connected. Then it is 0, 1, 2, 3, oh sorry, 0, 1, 2, 3, 4, 5. So 5 is connected to 1, so I'm writing 0, 1, 0, 1. Then 6, 7, 8, 9, 10 is connected, which is 1, 0, 1, 0. And 11, 12, 13, 14, 15 is connected, which is 1, 1, 1, 1. So now you can clearly see Z equals to 1 when it will be 1 when A1 A0 will be equals to B1 B0. Why? For the first case you can clearly see it is 0, 0 and 0, 0. Similarly, if I try to write for the second case, it is 0, 1 and it is also 0, 1. Similarly, for the third case, it is 1, 0 and this is also 1, 0. And finally, we have all as 1, so this it will again be 1, 1, 1, 1. So what I can write is clearly Z equals to 1 when, since this A1 A0 you can clearly see in the question is A, and B1 B0 is B when A is equals to B, which will lead to me option C. Any doubts in this? So this was a very good question, just to like clarify your concepts and your understanding and your power of thinking that how to proceed to solve a problem like this. Is there any doubt in this? Anyone?
No, sir.
Fine, then we can proceed. You can try this problem out. So this is a mux problem which was, I guess, in the weeks 4 assignment. So this was a very good problem. So that is why I have added this in this week, because I left it in the week 4 assignment. So maybe you have already done it. So maybe you can try it out. I'll explain it quickly and I will give you 2 minutes to let me know the answer, and then I'll try it out. Let me solve it by myself only because it might take some time then. So we, in the circuit given below, the propagation delay is given for each of the given components. So multiplexer, for multiplexer, NOR gate and inverter, basic, which is a NOT gate. So for multiplexer, the delay is 1 nanosecond. For NOR gate, it is 1.5 nanoseconds, and for inverter, that is not I'm writing, which is zero point 0.5 nanoseconds. If all the inputs are applied at the same instant, so all the inputs are applied at the same instant, we need to calculate the maximum possible delay. So we know in a mux what we have is the working is on the basis of the select lines. So there can be two possible cases, either t is 0 or either t is 1. So for t is equals to 0, we know that s equals to 0 will be selected. So the circuit will look like something like it will pass through this, and here s is 1, so it will pass through this, and finally we have a y. So a circuit will look like this for t is equals to 0. Similarly, if I take t as 1, so maybe I can use some different thing. So it will look like for 1, it will, this line will get selected, it will go like this. And since now here s is 0, so it will cross through this, and finally we have a y. So we need to calculate the delays in both the cases, and whatever will be the maximum delay will be the answer. So for case 1, the delay is, I'm writing it, maybe I can use the red ink only because of the case 1. So we are encountering a NOT gate, then the mux 1, then there is no delay, and finally we have a mux 2. So which will give us 1.5 plus 1 plus 1, that is 3.5 nanoseconds. Similarly, for second case, which we have denoted using blue ink, it will be not plus mux 1 plus nor plus mux 2, which is zero point 0.5 plus 1 plus 1.5 plus 1. That will give us 4 nanoseconds. So the maximum delay out of 3.5 and 4 can be 4. So the correct answer will be option B. So this problem belongs to, I guess, week 4. So this was a good problem which was left. So that is why I have covered it now. Now you need to find out, so we can proceed ahead, the gray code of these particular numbers. So here you can clearly see this is base 8. I will write, and the second number is base 16, that is B74 base 16. So you need to be clear about this basis. So maybe you can take 2 minutes, and if you get any answer you can let me know, and then I'll solve it. So let's try it out. This was a easy question. So first we will convert it to binary. and then we need to find the gray code of it. So again, keeping the first bit same, then 1 0 is 1. I'm doing the XOR option. 0 1 is 1, 1 1 is 0, 1 1 is 0, 1 0 is 1, 0 1 is 1, 1 1 is 1, 1 1 is 0. Sorry, 1 1 is 0, I guess, last. Yeah. Hmm. So now again doing the 3 bit. This is 7 1 4. Okay, so A and C are eliminated because it is 7 to 4. Similarly, we'll calculate because there are still two options. So B is A is 10, as you already know. B is 11. So 11 is we need to make the pairs in 4 now. So 11 is 1 0 1 1. That is 8 plus 2 plus 1. Yeah. 7 is 0 4 times 1, and 4 is 0 1 0 0. So again doing the gray code conversion now. So first bit remains the same. Then 1 0 is 1. 0 1 is 1. 1 1 is 0. 1 0 is 1. 0 1 is 1. 1 1 is 0. 1 1 is 0. 1 0 is 1. 0 1 is 1. 1 0 is 1. And finally 0 0 is 0. So making the pair of 4 now again. So we have 1 1 1, that is 8 plus 4 plus 2, that is 14. So C D E F, it is 12 13. So E is 14 and F is 15. So E is first. Then we have a 12, which is C, and then we have again a 14. So ECE base 16, which is option, yeah, option B. Is there any doubt in this?
No, sir.
Fine then. So again, this is a theoretical question that we have done similar. So let me do it quickly. So access3 code is both a sequential code. Okay, give me a moment. So access3 code is also sequential and self-complementary. So this is theoretical. So okay, so again we need to check the false statement. So this is correct. ASCII code of B is yes. So this one is shifted. Instead of here we have a one here from B. So this is also correct. Small b we will have a one extra here, which is also given. Access3 code for 0011. Yeah. So 3 is added to binary coded decimal. This statement is correct. The allowed values are from 3 to 12. Okay, so 12 is not given. It is 1100. So third statement is incorrect. Then the gray code is unweighted code with a unit distance. Yes, because there is only one bit change. So it is unweighted with 1 unit distance. And then it is also a reflected code. So yeah, so this is also correct. And binary to gray. Okay, so this is the similar option as we had in this option previous question. So third and fifth are incorrect. That will give me B as the answer. So I've done it quickly because this is purely theoretical. I don't want to waste much time on that. So maybe we can, yeah, so this is a good question. So the output Y of a 2-bit comparator is logic 1 whenever the 2-bit input A is greater than 2-bit input B. So whenever A is greater than B, it is saying the output is 1. The number of combination for which the output of logic 1 is, so we need to find out how many number of combinations are possible. So this is a good question. So maybe you can try it out. You can take 2 minutes if you can get some answer. So you should know that this is a 2-bit comparator. That is, this will be A1 A0 and this will be B1 B0. So let me know if you get any answer, or otherwise I'll try it out after 2 minutes. So let me also try it out with you. So as you know, so we have a overall 4 bits, so we can have 16 combinations. So let me write them. So it can be 0 0 0 0 0 0 0 0 and 1 2 3 4 5 6 7 8 and 0 0. So now you can clearly see we have certain cases. We have certain cases when we will have equal number of this. So this is A equals to B. This is A less than B. Similarly, we will have certain cases. So let me write in short. Now the question is asked 2 bit is greater than 2 bit of B. So it is possible when let's say we have a 1 1. So it will be possible when it is 0 0, when it is 0 1, when it is 1 0. So this is the case. So A1 is 1 1 here in 3 cases, and these 3 are the cases for that. Let's say where we have a 1 0, which is these number of cases. It is possible when we have a 0 0 and 0 1, because rest two of them are 1 1 and 0 1. So 0 0 and 0 1. It is also possible when we have a 0 1. So these 4 cases are there. So it is possible when we have a 0 0, rest are equal or either smaller. So there are total 1 2 3 4 5 6 cases in which A is greater than B, or A1 A naught is greater than B1 B naught. So this is also given by a shortcut formula for a n bit comparator. Total cases for A greater than B is 2 raised to power 2n minus 2 raised to power n by 2. So here we have n as 4 because we have 4 bits. Sorry, we have a 2-bit comparator. So we have n as 2. So for A greater than B, you can clearly write in the formula 2 raised to power 4 minus 2 raised to power 2 by 2. This will give 16 minus 4, that is 12 by 2, that is 6. Similarly, for A less than B, we have 2 raised to power 2n minus 2n by 2 as the formula. And for A equals to B, the rest of the combinations, sorry, are A equals to B. And the total combination possible, we already know for a 2-bit, we have just checked, it is 2 raised to power 2n, that is 16 combinations. So this is a very important concept. It helps a lot if you already know the formulas in shortcut. There are various questions in GATE also that have come on this concept. So for A greater than B, there will be 2 raised to power 2n minus 2n by 2, which is also equivalent to A less than B. And for rest of the cases are A equals to B. So in this we have 16 combinations, as we already know, out of which 6 are A less than B, 6 are A greater than B, and remaining 4 are A equals to B. Is there any doubt in this? Okay, so the output Y of the 2-bit comparator analogy. So number of combinations. So the right answer to this question will be 6, because it does not have any options. So 6 will be the right answer. So this is a gate question, similar gate question, which was a numerical type question. So that is why there is no option. So if you understood this particular question, you can try this out because it is exactly similar. And this was a gate question of some recent time. So maybe you can take 5 minutes and let me know the answer to this. So again, it is similar. We have two 2-bit number that are A and B, given as input to a 2-bit comparator. Again, the comparator PQR are the outputs PQR, and PQR are basically belonging to 3 cases. Then for the circuit shown below, probability of S2 being 1 will be what? So this is a very good question. If you have understood the previous question, then you will be able to solve this out. So maybe you can take 5 minutes and let me know the answer. So let me try to solve it out. So we had this again, a similar 2-bit comparator is given. So here the question is are the probability about the probability of S2 being 1. So this is a 3 cross 8 decoder, and we already know in 3 cross 8 we have PQR as given in the question, and we have 8 outputs which will be as given in the question S0, S1 to S7, and we can have 8 cases. So if I try to make it out simply, so we can have 8 cases that are S0, S1, S2, S3, 4, 5. Okay, let me make a bit bigger. S0, S1. So PQR. So basically we have 8 combinations of the 8 3 cross 8 decoder. So now the question says when S2 is 1. So S2 is 1 when P is equals to 0, Q is equals to 1, and R is equals to 0. And here you can clearly see we have 3 combinations. So P is 0, that is A less than B. So Q is 1, means A is greater than B, and R is 0 when A is equals to B. So we need to calculate the probability of S2 being 0 by this combination now. That is when A is, sorry, this was what? When A is greater than B, right? So we have just found out that for a 2-bit, there are two bits magnitude. So there are total 2 raised by 2n combination, that are 16 combinations, out of which for A greater than B we have 2 raised by 2n minus 2 raised by n by 2 combination, that is 6. So the probability here of S2 being 1, sorry, is equals to probability of A greater than 0, that is the total combination possible, by the total combination when A is greater than B. So we have just found out the formula in the last problem only, so which is 6 divided by 16, that is 3 by 8, that is point 3 54 60 7 56 5. So this is the probability there of S2 being 1. So the correct answer up to 3 decimal places is 0.375. So this was a great question, I which was very good in terms of the knowledge acquired, and also here you get to know that how many combinations are possible in a 2-bit magnitude comparator. And again we know that the total combinations are how, and we also get to know some concept of decoder also. So including all these things, we have wrapped this question up. So is there any doubt in this question? Please let me know if you have any doubt. Okay, so I'm assuming if you don't have any doubt, so let's proceed. So this is a very easy question. Maybe you can take 2 minutes and let me know the answer. Okay, so we have two half adders in this question, and we already know that sum of the half adder is XOR and carry is the AND operation. So we have the input of the next half adder as the AND term. So S1 is basically, if I open it, it is A complement B plus AB complement, and and C1 is AB. So the input, let's say this is Z. So Z is the multiplication of these two. So I'm doing the same. So here multiplying this A with A complement will reap 0, and here also B with B complement will reap 0. So Z will be 0. So the input to this half adder, both of them will be 0. So S1, sorry, now S2 will be 0 XOR 0, and C2 will be 0 times 0. So this is also 0 and this is also 0. So the final output will be option D. So is there any doubt? Okay, so if there is no doubt, then we can move ahead. Okay, so now we have some questions for error detecting codes. So which is one of the code is the Hamming code. So Hamming code has its certain relation. So in the question it has been asked how many check bits are required for the data word of 25 bits. So we have data bits, we have total bits. So the relation of for the Hamming code is given by 2 raised power k is should always be greater than m plus k plus 1, where m are the data bits and k is basically check bits. So here we need to go from the minimum to the maximum option because of the power consumption criteria. So whatever minimum value will fulfill this condition will be the answer for the check bits required for the data word of 25 bits. So we'll start with 4. So the relation is 2 raised power k greater than m plus k plus 1, and m is given out to be 25 here. So you can clearly see the data word of 25 bits. So let me write, so 2 raised power k greater than 25 plus k plus 1, which will give 2 raised power k should be greater than 26 plus k. So for k is equals to 4, which is the first option, this will give me 2 raised power 4 is greater than 26 plus 4, which implies 16 is greater than equals to 30, which is wrong. So let's move ahead to the next option. For k is equals to 5, it is 2 raised power 5, which will be 26 plus 5. Now 2 raised power 5 is 32, will be greater than equals to 31. So this is correct. So we only need now 5 bits, 5 check bits are required for a data bit of 25 bits. So in Hamming codes, we can clearly see now 5 bits are required for a data bit of 25 bits. So let me know quickly if you understood the concept. How many bits are required for a data word of 27 bits? Quickly let me know the answer in maybe in 2 minutes because this is very easy. If not, then I'll solve it out. Again, the relation will be 2 raised power k should be greater than m plus k plus 1. Options are same 4, 5, 6 and 7. So quickly let me know the answer in 2 minutes, otherwise I'll solve it out. Maybe you can write 28. So let me also try it out directly. So for n equals to 5 that we have checked in the last options, so this is 5 plus 1. So 32 is greater than equals to 34 is coming. So this is wrong. So we'll go for k is equals to 6. This will be 2 raised power 6 should be 29 plus 6, that is 35, should be greater less than equals to 2 raised to power 6, that is 64, which is correct. So here 6 check bits are required. So I hope you understand the problem of check bits for the Hamming code. Is it clear? Any doubts? Okay, fine then. We can try. Okay. So this is again a theoretical kind of question. So the question says now the code used to reduce the error due to ambiguity in reading of binary optical encoder. So always remember, code used to reduce any error or ambiguity is always a gray code. So the correct answer will be option 3. So I'll let you know why always gray code, because here you can see. So here you can clearly see why gray code, because in the binary code you see that this is a bit, so this is the 1. So here the bit changes, we have a 1 bit change. Here now we see from 1 to 2 what we have is we have from 0 1 we have changed to 1 0. So here we have a 2 bit change. So now again if I see for even the octal code, so this is 0 0 1, it is 0 1 0. Here we have a 2 bit change. But if you see even the access 3 code, here we have a 0 1 0 1, here we have a 0. So clearly see the 0 1 is getting 1 0. So here also we have a 2 bit change. But you clearly see in the gray code there is always a single bit change. So let's say from 0 0, here we have 1 bit, from here we have 1 bit, here also we have 1 bit, here we have 1 bit, here we have 1 bit, and then we have here also 1 bit. Similarly it is here also 1 bit, and this is also 1 bit. So that is why there is always a 1 bit difference in the gray code, which makes it superior than any other code. So that is why, to reduce any error or any ambiguity in the reading of any encoders or any others, we need to reduce the error using only and only gray code. So is there any doubt in this? So let me quickly summarize out the things that we have covered. So we started with the last question of that previous lecture of the complement part, and then we have covered a lot of magnitude comparator questions. Basically, we studied about 2-bit magnitude comparator circuit initially, and then we read about how the ALU block work and how can you solve the problems from the ALU block. Similarly, we read 4-bit comparators and some of the important relations. Then we did a few questions on binary to gray conversion and binary to octal conversion also, and then we read about, then we read about the IC, what was the IC 7485, and then we did a very good question on the basic total combinations. Sorry, this was a question, I guess. Yeah, this was a question on total combination, and we derived certain formulas, how it is coming out to be 6 out of 16, and how what are the number of combinations for equals to b, greater than b, and less than b, which helped us in solving this gate question also, which is a 2-bit comparison question, which is merged with a 3 cross 8 decoder. And then we moved ahead to certain half adder questions, and finally we did certain error and detecting code questions, which was all the topics of this week 6. And we already know that in, so yeah, there is only a 1 bit difference in this gray code, whereas rest of them have 2-bit difference. So we, gray code is always superior in error control as compared to any other code. So this is how we ended up the lecture, and also we have covered, as you can see in the course outline, we have completed the combinational part, and from the next week we will be starting the very important part, that is the sequential part of this particular course. So we have wrapped at this particular part, that is this particular part is completed now, the combinational part. So based on the knowledge of this combination logic, we'll be covering the subsequent topics in the further weeks now, which is the most important part, that is the sequential circuit. So I hope now you have a good understanding of each and every combinational part of the circuit, so that we can move ahead to the sequential part in the subsequent lectures. I hope it is clear to you. And now we will be meeting on next Tuesday, because I have taken the extra class this week only. So if you have any doubt, you can again post on this email, and this lecture will be posted by today only on the YouTube. You can have a rerun on the recording. So with this, we can wrap up this lecture for today. So if you have any doubt, you can ask. Do you have any doubts? So if you don't have any doubt, then we can wrap up the lecture. Thank you for joining, everyone whosoever have joined.